All right. Very well. I think we can start. So we are also online. We will transmit this on YouTube. Okay. So let me do a short introduction. Good morning, everyone. Good afternoon also. Welcome to another talk in our webinar series. Today we have Dr. Tilman Troester from the Royal Observatory, Edinburgh, and he will talk to us today about cosmology with the kilodegree survey. This webinar is also being streamed live on YouTube. So if you can find the link on our website, or you can access it directly on YouTube using our channel /LIneA MCTI. So Dr. Troester, thank you very much for being with us today. And the floor is yours.
Thank you very much for having me.
Okay.
Is that working?
Yes, we can see your screen. Thanks.
All right. So I'll talk a bit about recent results we got from the kilodegree survey, and mostly focus on the cosmology results there. So to start with, what's KITS? So KITS is the kilodegree survey. It's a survey, wide field survey optimized for weak lensing. It uses the VST, and at the moment we have finally 1,000 square degrees analyzed. So we finally do the kilodegree part of the name. That's almost a full survey, so we still have a little bit left, but it's almost there in terms of what we can get out of the science terms. So at the moment, you have about 21 million galaxies that you can use. What makes KITS unique among the other weak lensing surveys that we have full overlap with infrared. So we have 9 photometric bands across the whole survey footprint, which gives us quite a lot of confidence in our photometric redshift calibrations. So what are we actually trying to measure? So the main probe that we use in KITS, because it's a weak lensing survey by design, essentially, it's something called cosmic shear. The idea here is that we want to infer the matter distribution by how light is deflected by the intervening matter. So conceptually, it's somewhat similar to trying to figure out what the surface of the water looks like just by looking at the ripple of lights at the bottom of a pool. In more practical terms, we're looking at correlation between galaxy shapes. So if you have some faraway background galaxies, and let's assume they're circular, then as the light passes by foreground matter distributions, that light gets deflected, and the image of these faraway galaxies gets distorted into ellipses. Now, what cosmic shear does is looks at the correlation between the shapes of these background galaxies. And from that one, I can infer what the foreground distribution of matter is. Now, it's not the only thing you can do with this, because we have some idea where the matter in the universe is distributed. So we know if there's a heavy galaxy, then it's probably dark matter around that. So what we can do is we can look at the cross correlation between the galaxy's position and some background galaxies. That's called galaxy-galaxy lensing. That's that you look at the correlation how the shape of background galaxies align with known matter distributions in the foreground. And finally, you can just take known galaxy positions, and because you know that these sit somewhere in potential wells and in the matter distribution, you can infer directly from that also what the matter distribution looks like. That's just looking at the positions, the correlation of positions of galaxies. And what's done nowadays is to roll all of these statistics into a joint analysis. And because these are all 2-point statistics, that's called 3 times 2 point. And that's a joint analysis of cosmic shear, so the correlation between shapes, the galaxy-galaxy lensing, which is the correlation between galaxy position and shapes, and galaxy clustering, which is the correlation between galaxy positions. Now to the actual data we're using. I think I said that the main part of that whole exercise is cosmic shear, and for that we use the kilodegree survey. For the galaxy lensing part, we use a spectroscopic sample for our foreground galaxies. It has some advantages. For one, we don't need to worry about the photometric uncertainties of these lensing galaxies. And for that, we use the overlapping BOSS galaxies in the north patch of KITS, and in the south, we use 2DF lens, which is also a spectroscopic survey that was designed to be quite similar to BOSS. We have overlapping spectroscopic surveys for the whole KITS 1000 footprint, essentially. And finally, to complete that triangle of 2-point correlations, we use the full BOSS year 12 footprint for the galaxy clustering measurement. So to give you an idea on where these surveys lie on the sky, so KITS has 2 patches. One is in the north equatorial and one's in the south. As I said, the north part here overlaps with BOSS, whereas the southern patch overlaps with 2DF lens. So we have that full spectroscopic coverage in addition to the infrared coverage I mentioned before that really helps us out with the high redshift calibration of our background galaxies. So over the last summer or into the fall, we had our basically series of KITS 1000 core papers. So we had the cosmology results based on just cosmic shear, the combined prop analysis, and then going beyond just the flat lambda CDM model, and then a set of methodology papers on looking at the modeling and theoretical methodology, the photometric redshift calibration, and the shear calibration measurements. But here I'll just talk about or mainly focus on the cosmology results that we got out of KITS 1000. So first looking at the cosmic shear, because we have, as I said, this infrared coverage on all our galaxies, we can push our redshift calibration to quite high redshifts. So using our analysis is 5 tomographic bins between redshifts of 0.1 and 1.2. The redshift distribution is shown here on top. What we're doing a bit differently than before, and what others are doing, is we're looking at the number of different 2-point statistics on how we can measure cosmic shear. So the first one is the known correlation functions, where you look at the correlation of a shape here on the sky and here parameterized by the distance, angular distance between them. Then there's something called Kosebe's, which is essentially a linear transformation of these correlation functions, such that one can optimally distinguish between E and B modes, where E modes are what is caused by gravity, or in other words, you wouldn't expect gravity to create any B modes. So if you measure any B modes, it's a clear sign that there's some systematic that's creeping into your measurement. And finally, we also look at band power. So that's the angular power spectrum, which has the advantage that it has very clearly defined physical sensitivities caught directly in the angular multipoles. And because all these different estimators pick up different parts of the noise spectra and are sensitive to slightly different systematics, it gives us a lot more confidence in our constraints we get out of our measurements. On the theory side, our baseline cosmological model is flat lambda CTM, a very fixed neutrino mass to the minimal mass of 0.01, 0.06 electron volts. To deal with the nonlinear modeling, we use HM-code. It has the advantage that we can model and marginalize over varying feedback. So the effect of baryonic processes like HN feedback that blow out gas out of galaxies and therefore suppress the growth of structure and suppress the matter power spectrum. Then we also model intrinsic alignment. It's quite a simple model, but I think for cosmic shear, we're still sufficient in this case. We marginalize over uncertainty in our photometric redshift calibration, and we include uncertainty in our shear calibration directly into covariance. And so using this and then our data, here's the result for the cosmic shear band powers. So the top left triangle is the E mode. So where the signal is, on the bottom triangle are the B modes. So that's what you would expect to be consistent with 0. And the pink line is the best fit model. And as I said, we use 5 tomographic bins. So you have the 5 the autocorrelations and the cross correlation between these 5 tomographic bins. And taking this, we can translate that into cosmological constraints. So on the left, we have that well-known cosmic banana that's parameterized in sigma 8 on the y-axis here, which measures basically how clumpy the matter distribution is, and omega m, which tells us how much matter there is. Because reglancing can't really distinguish between those 2 effects, we have a very long degeneracy. But across the degeneracy, that's a parameter called S8. There we have quite good constraints. What's shown here is the constraints from our 3 estimators. We have the correlation functions in cyan. We have the Kosebe's in orange and the band powers pink. And you can see that all of them are very consistent in the direction that we can actually constrain, whereas the direction along the degeneracy is essentially unconstrained. So any noise fluctuation just pushes you up and down that banana, because these different statistics have slightly different sensitivities to where they pick up noise that basically pushes us around along the banana. But that's completely expected. We did tests on a lot of mock surveys, and that scatter is nothing out of the ordinary. And in red, we have the Planck 2018, so the legacy results. And the agreement or disagreement in S8, so the direction that we constrain best essentially, is about 2 to 3 sigma, depending on which of the statistics and parameter combination you look at.
Can I ask a question?
Oh, please, yeah, just ask it.
Would you expect that, so usually the correlation functions in real space or the power spectrum in harmonic space, they should have more or less the same amount of information. Now, looking at your plots, I see that the correlation functions in real space it has a larger constraining power than the band powers in harmonic space. Do you have any intuition of why is that happening?
Yeah, so what's plotted here is S8, which is given here at the top, which is a good description of the degeneracy direction, but it's not perfect. So basically, this correlation you see here, for example, in the band powers is just the fact that the exponent here, like the square root, isn't a perfect descriptions of this degeneracy direction. If you use something what we call sigma 8, which essentially just fits the best fit or the direction in this polarization that is best constrained, so vary the exponent here around 0.5, then all of these probes are very similar. So that goes away. So these differences here is really just the fact that S8 isn't a very good descriptor for band powers. Well, it is happens to be a very good descriptor for the correlation functions.
Okay, and just one more quick question. So I understand the 2-point correlation function is in real space, the band power is in harmonic space. What about Kosebe's?
Right, so these are something in between. Right, so this is something called modes. There's no very good physical interpretation. Essentially, the n equals 1 mode is mostly like the overall amplitude, and then higher modes have a finer feature that you measure in the correlation function. So most of the information for cosmic shear is contained in the one node, because cosmic shear really doesn't have any features in what they measure. So think of it as roughly like a Fourier transform of the correlation function-ish, where higher modes pick up basically small features in the correlation function.
Thank you.
Any other questions about the cosmic shear stuff before I move on to the joint analysis? All right. Then for the 3 times 2-point model, so the joint analysis, we basically use the same setup as for cosmic shear, but because now we have that spectroscopic sample for the galaxy-galaxy lensing and for the galaxy clustering, we also add in a full-shape interpretive model for what are essentially the boss galaxies. So for the systematics, again, because it's a joint analysis, we have the same systematics that we use for cosmic shear. But on top of that, we have the nonlinear bias model for the spectroscopic galaxies. We deal with redshift space distortions and also with magnification. So the magnification is a fixed parameter that we calibrate on simulations. So for the galaxy clustering measurement, as I said, we use the full bus DR12 footprint for that. And specifically for the estimator, we use what's called correlation function wedges. So that you take the anisotropic correlation function measurement in real space and then basically chop that up along the line of sight and perpendicular to it, and then some intermediate direction. So you measure the
Pizza.
What's your question?
Sorry, just
Que colher? Ó, lapate dessa, ela quer epinar. Ó, no preparão, lapate.
just a minute. Mariana, could you please close your microphone? Thank you.
Sorry, guys. I'm with my 2 kids here. I'm really sorry.
No.
Thanks, Brian. Sorry, please go on, Dr. Troester.
Right, so we have our correlation functional batches, and for that we use that full shape model that I described. To note here that it's exactly the same model that was used in the BOS-DR12 analysis by Ariel Sanchez. So we reused the exact same measurements as well as the model. So there's, for the galaxy clustering, there's nothing new in that sense. For the galaxy lensing, so we use the BOS galaxies on the overlap in the north and 2DF lens on the overlap in the south. And the measurements here are shown on the right. One thing to note is that a lot of it is grayed out, which means we're not actually using that in our inference. The reason for graying out in the certain angular multiple ranges is that because we use that perturbative model for the galaxy bias, we can only push that to a wave vector of like 0.3-ish h/megaparsec. And above that, we don't have a good enough model, belief to really pushing that nonlinear bias regime for the galaxy lensing. Hence, we need to discard that small scale, angular small scale information. So it's basically these parts here. And furthermore, for the cases where we have galaxies in front of the lenses, there's obviously no lensing signal because they're sitting in front of the galaxies. So their intrinsic alignment is really the only contribution to the signal. And while we believe our intrinsic alignment model is good enough, where the sources are behind the lenses and intrinsic alignment is a small part of the lensing, total lensing signal. In the case it's the only signal, so when they're in front of the lenses, we believe our intrinsic alignment model is a bit too simplistic, and we don't entirely believe what we can get out of it there. We reject the bin combinations where the sources are in front of the lenses. But yeah, the take-home message is that given our modeling and our trust into it, we are quite limited in how much of the big data vector we can actually use robustly. So these are the constraints we get. So in pink is again the cosmic shear result that I showed you before from the band powers. If you add on top of that the galaxy lensing, you get the dark purple constraints. And as I said, even though we put in a lot of effort to get the modeling and the methodology for that right, because we have to discard that much of the data, that doesn't actually help us much. And in blue is the full BOS-DR12 footprint galaxy clustering constraints and the full chip analysis. And if you combine everything together, we end up with the red contour, which is our fiducial kits 1000 310 2-point result. We can compare that to what other surveys have found. So for example, here in yellow is the DES year 1 3 times 2-point result. You see we're in very good agreement with them. But also Planck, and there the agreement is a bit less good. So to summarize, if we only care about S8, because we say that's basically the parameter we constrain best with lensing and we're primarily lensing survey, then while you have similar precision of parameter as Planck, which is like about a 2% measurement of S8, we find that we're about 8% low, which translates into like a 3 sigma tension with Planck in S8. Now, if you take the full parameter space, because you could make an argument that you should cherry pick a single parameter if there are other parameters that agree perfectly well, then the tension is about 2 sigma. Are there messages in the chat? I'm not sure I can see from Yeah. All right. Are there any questions so far about just vanilla 3 times 2 point results I've shown so far?
Hey, quick question here. Can you hear me?
Yeah.
So, and I presume the results that you're showing for the 3 times 2 is the combination of the band powers. I mean, the angular power spectrum only.
Yeah.
Do you have comparisons for 3 times 2, like using then Kosevis for the clustering, for the shear part, and maybe 2-point functions also for the clustering part?
No, we didn't look at that. So we had our band powers. When we set out the methodology, we choose the band powers as our fiducial estimator because it had that very clear physical scale separation that allowed us to say we don't trust certain galaxy bias ranges, so we can discard that and discard things because of parent feedback, and we can't do that with correlation functions and Kosevis because there the support in L for a specific mode or angular range is quite wide. But it wouldn't change much. So because you see here, the galaxy clustering essentially constrains omega m. So you just cut that S8 omega m shape somewhere on a specific omega m.
So I also have a quick question. For the galaxy clustering, you have spectroscopic data. But did you also bin? Did you also use redshift bins, or how did you do that?
Right, so we use 2 redshift bins. Yeah, so it's basically we took the BOSS DR12 combined sample with the two redshift bins. And we use the same redshift bins for galaxy lensing and for the clustering.
Thank you.
If I can also ask us a very quick question. You mentioned that you're also using the overlap with 2DF, with the 2DF survey, spectroscopic survey, am I right? But you only mentioned BOSS. Am I confusing something? I don't know.
Right, so for the galaxy lensing, we use both BOSS for the north part and 2DF lens for the southern part. But for the clustering, we only use BOSS DR12. But we use basically all of BOSS DR12, so that swamps any clustering measurement and signal to noise that you would get from 2DF lens.
Okay, thank you. I'm sorry if I missed that before. Okay.
I didn't mention it, I think. Right, any other questions? All right. Well, as I said, we have about a 3 sigma tension if you look at a single parameter and like 2 sigma tension if you look at the whole parameter space. And now, depending on how comfortable you are with unlikely events, you can either say, well, that's fine, or someone messed up with the systematic treatments. But assuming that Planck did everything right and we did everything right, then you might ask, well, maybe our flat lambda CDM model with fixed neutrino masses is just a bit too restrictive to describe both data sets. So to recap, the standard model that we use is we fix a minimal neutrino mass. We assume that the universe is basically flat. But neither of those is really intrinsically required. Then we assume general relativity and a cosmological constant. Now you can ask what happens if you relax any one of these assumptions. Starting with the neutrino mass, as it's well known, it doesn't do much to cosmic shear. So that it doesn't do anything here to the S8 tension. Here, we get very weak constraints on the neutrino mass. The fact here that it pulls to what appears to be high and potentially non-zero neutrino masses is that just quite general effect of all these low redshift surveys finding a low amplitude of clustering, like a lowish sigma 8, and the neutrino mass basically tries to counteract that, and therefore you pull to higher values. So like if you look at similar chains for DES or HSC and so on, they all find that they pull to the higher neutrino masses with quite similar constraints, or a lack of interesting constraints, considering the recent scattering results. Then moving on, removing just the assumption of flatness. There has been quite a lot of fuss over the last year or two about preference in Planck for a negative omega case. So we try to do that as well, just that our data by itself without including Planck, because we say we see attention as Planck, so we're not comfortable combining with Planck. So all the results I'm showing here is really just kids plus by themselves. One thing we noticed that H0 priors matter quite a lot. So if you just take the fiducial Planck chain as they distributed, they have a very wide range of H0 that they allow. But for our analysis, we constantly decided to restrict ourselves to reasonable values of H, just because cosmic shear by itself can't constrain it. So what we do is we take the Planck constraints and subtract -5 Planck sigmas on the low end, and take the Rees et al. CFIT supernova results and add +5 sigma of theirs for the we call a reasonable prior on what we believe H0 is. And if you restrict basically the Planck data or the Planck chains to that range, then you pull everything in a more reasonable shape. So before it looked even worse, you can barely see the dashed line here, which is the fiducial Planck chain. But if you impose a reasonable H0 prior, you pull things together again, and also get a much tighter constraint from Planck around zero curvature. But there's nothing interesting to see here from our side. It's the summary here. Then you can say, well, maybe a cosmological constant is a bit too simplistic. Let's vary the equation of state of dark energy. So that's WCDM. And again, H priors matter. So that's the difference between the dashed and the solid gray curves for Planck. But you might have noticed, if you look at S8, it looks like we're good now, because in S8, the agreement is now much better between the 3x2-point results, Planck, once you allow for freedom in WCDM. But it isn't an indication that WCDM is a pretty good model, because our constraint here in W is at smack right of -1, which corresponds to lambda CDM. And furthermore, if you look at the joint constraints of our new parameter, which is this W, the equation of state of energy, and S8, see that in this parameter space, they don't actually agree with each other at all. It's just once you project this along S8, you have that projection effect that seems like an agreement. But if you just look in this S8W space, the tension is still 3 sigma. But if you take the whole parameter space, you're still at 2 something sigma tension as before. So adding that freedom of varying the dark energy equation of state doesn't really resolve the tension between Planck and the low redshift measures we do. And finally, we looked at the modified gravity model. So we look at an F of R model, and it was mostly a proof of concept because we used a fully nonlinear modeling for the matter power spectrum, so we can use the full cosmic shear constraining power essentially, which hasn't been done before. But unfortunately, because we have to marginalize over all these other systematics like baryonic feedback and redshift uncertainties, we don't actually get constraints on FR naught from Kitt's data alone. So this is basically the parameter shown here. But we showed in forecast for something like Euclid or LSST, the Rubin Observatory, then at that stage, we can also get quite strong constraints on modified gravity, FR and modified gravity. The note here is we didn't do this with the Schrems 2-point results or the data vector, because at the moment this code only does the matter power spectrum, so we don't have a corresponding bias model. Because we want to have a consistent modeling, we choose to stick with just the cosmic shear constraints here. So to summarize, we find that the basic fiducial model we used before, so minimal trino mass, spatially flat lambda CTM, that works perfectly well for our data. There's no indication that any of these models works better or worse than the fiducial model. And with exception for the WCDM case, the tension with Planck and S8 persists essentially unchanged. And even in the WCDM case, once you look to more parameters, you see it doesn't really help the overall situation. In that the WS8 tension is still 3 sigma, and the overall parameter space tension is still at 2-ish sigma. Right. Any questions so far on these experimental models? Okay. So after looking at models that extended Bayesian flexibility, we tried to do the opposite as well to see if that does anything. So this we looked at what we're actually measuring. And as I said before, we basically only constrain S8, which is the amplitude parameter that scales the amplitude of our signal. And because that is proportional to the matter power spectrum, that's in principle proportional to the primordial power spectrum that Planck measures. So Planck parameterizes the amplitude of the primordial power spectrum by AS. But if you look what constraints we get, is that lensing or the low redshift universe constrains AS quite poorly. If you look at just the tension in AS, which is also, you could argue, an amplitude parameter, the tension is also quite a bit lower. So what lensing constraints is this S8 parameter, which is a combination of sigma 8, which is a complicated function of the power spectrum, which in turn depends on AS, other parameters, as well as omega m, so the amount of matter in the universe. So clearly that's a complicated function of the primordial amplitude of the power spectrum and a whole bunch of other parameters. So we said, considering that our constraints on AS that we get from lensing are quite weak, let's just fix that to the best fit Planck value for AS and see if that resolves tension. So if you fix the overall amplitude, then you could expect that that fixes S8 as well. But surprisingly, it doesn't really do much. So once you fix AS, because you still have all these other parameters that can affect the amplitude of the lensing signal, you have quite a lot of freedom to restrict before you run into any problems. So in pink here is again the fiducial cosmic shear results, and once you fix S8, you're still on this banana. You just basically restrict to some subspace in omega m and sigma 8. But the tension in S8 here, that one is essentially the same. So you're getting slightly tighter because you break some of that omega M S8 degeneracy. So it's basically a leftover because S8 is in the perfect descriptor of the degeneracy direction. Break that, but because you move up, but also shrink the tension here with Planck is the same 3 sigma as before. But what it does do is, because before omega M and H and so on were quite independent, once you restrict yourself to that specific primordial amplitude, now you're sitting on a very narrow degeneracy between H and omega M and H and sigma 8. And because you are restricted like that, it pulls you around a bit, especially in H. So because clustering basically measures omega M, but now you have that degeneracy imposed by that fixed amplitude between H and omega M, you end up with an H constraint from clustering that seems to be quite a bit better in agreement with Planck. Or again, that is really just an effect of these different degeneracies that you caught on a specific point. Finally, you can ask, well, you looked at a whole bunch of models. Are any of these models better than any of the others? Like even if you don't find a preference, or like let's say an omega, a W of -2 or something like that, is WCDM, let's say, better descriptions of the data than lambda CDM. We looked at a number of model selection criteria. It's a range of how easy they are compute versus how Bayesian they are. Starting with what's called the D-mean situation criterion, which essentially compares the best fit chi-square between models. So compares the increase or the improvement in chi-square with the number of added parameters, simply speaking. Then there's the Watanabe-Akaike information criterion, which is similar to the DIC, but it doesn't rely on the point estimates where you compute these chi-square values, so it's a bit more Bayesian in that sense. And finally, we look at the Bayes ratio, so the ratio of the model evidences between the models, which is arguably the correct Bayesian ways to go about things, but it's challenging to get robust evidence estimates. But over all these different model selection criteria, we didn't find any significant preference for or against any of the models we looked at. So in that sense, that exercise was quite boring in its outcome, but goes, I think, well with what others have found so far. So to summarize everything, we found no indication of physics beyond flat lambda CDM. The lambda CDM we found sticks with the same 3 sigma tensionless Planck that we have found in previous lensing surveys and low redshift surveys. And we try a lot of things, and that tension seems to stick around. And I'll leave you with this. Thank you very much.
Thank you very much, Dr. Troester, for the very interesting talk. We now still have time for questions from the audience. If you joined us on YouTube, please put your questions in the comments and I will redirect them to our guest. So, questions?
Hi, Tilman. Thank you very much for this amazing lecture. It was really nice. So I would like to ask you a little bit about the intrinsic alignment models you consider in your work. Can you talk a little bit about this?
It's really just a run-of-the-mill non-linear linear alignment model bright linking. So it's arguably pushing it a bit, but we found that for the cosmic shear results, it's probably still good enough. I didn't see any evidence for it shouldn't be working, but especially for the galaxy lensing, as I said, it wasn't good enough to make use of the data we have in hand.
I see. Thank you very much. Congratulations again. Thank you.
Thanks, Felipe. More questions?
So I have a question also. So the covariance matrix that you used is an analytical covariance matrix, or is it based on simulations?
It's analytical.
Okay, thanks.
Hi, this is Bruno from UFRJ in Rio. Thank you for the talk, Tilman. I'd like to ask a bit of a technical question about the S8 parameter. So I was reading on it recently, and if I understand correctly, it's from Jane and Celiac analysis, and I see how they do it by looking at the power spectrum and doing some approximations to the redshift distributions. But you don't use the same estimator, I guess, that they use in the original analysis. And you also don't use the same redshift range, which is kind of, I guess, what the reason the degeneracy kind of rotates. So I guess my question is could you clarify, please, a little bit, how does this degeneracy work on those different estimators? You mentioned that in the 2-point correlation, it works better, but it's not the same estimator as the original paper. Then you mentioned the sigma 8. I don't know what the paper is for this, but could you please comment a little bit on why not try a different combination, and how does this work with the estimators that you use?
Right. I mean, S8 is just a convenient way to summarize weak lensing results because it's quite close to the degeneracy direction. As I said, if you take this relationship but replace the square root with a power law and fit the power law exponent, and then we end up with power of 4.57 or 5.6, something, I believe, for the band powers. So it's really quite close to like the square root. It's just like a bit shallower. We could probably do something similar. There has been a recent DS tension paper where they used these eigentensions, I believe. I think it was presented in some earlier paper. But as you look at the directions in the posterior that are best constrained, and you end up with something similar like S8 again. So I think S8 is really just a convenient number that you can compare across surveys because it's around half in the exponent. Whereas if you start fitting the best fitted degeneracy direction, it will be different between different surveys and different estimators, which makes it then hard to compare numbers. But if you care about the best constraint direction, that's what you would use. And if you use that in this case, in kids, you get that these differences here basically go away.
Okay, as a quick follow-up question, do you have an intuition for why the estimator of the 2PCF works better with this particular estimator? What is the feature in the data that is picking that helps constrain in this direction?
No, I would personally guess it's just a question of a noise realization. So it might be interesting to go back into the mocks and see how the exponent varies with different mock realizations. but we didn't look into that particularly. We were more concerned about how estimators of a particular parameter vary between different noise realizations.
Okay, and if I may just abuse my speaking rights and ask another follow-up question still on this, why is it that the BOSS, this is a weak lensing type of parameter, right? But it seems to work really well also with the spectroscopic data, right? It's orthogonal, it's vertical, but it's also very non-degenerate, right? And there, yeah, exactly, the left-hand plot. And I found it was a little bit surprising based on what I know about the physics of how these parameters go in the P of K, right? So do you have an intuition for that too?
No, I mean, if you remember if you look at because my mouse has disappeared this. If you look in this omega m sigma 8 parameterization, if you just look at the clustering by itself, then that's, I think sigma 8 and omega m are quite independent there. So it's, I think it's just, it happens to work out to also look quite independent in the sig S8 omega m direction. But no, I don't have like a physical interpretation on what comes through. I mean, these full shape lambda CDM constraints also look quite different than the constraints you get if you look just at the F sigma 8 and the BO feature constraints you get into the main BOSS papers, like the BOSS papers.
Okay, thank you very much.
Thank you. I think we still can accommodate another question. Okay, well, I have a question that it's not about cosmology, but it's about the survey itself. You showed in the beginning that there is a region close to the zero declination part of the sky that the survey observes. First, how do the data rights work? And second, did you try to identify solar system objects or some solar system signs in this part of the survey?
Right, so the KITS data is all public now. So the raw imaging data it's an ESA survey, right? So that one is public, has been public for quite a bit. And we made the whole shear catalog, everything available with acceptance of the CITAMS 2.0 paper. So these are public now as well. So if you want to play with the data, please go ahead, poke around in it, see if you find anything that you missed.
Do you have any idea of the size of the pixel or the astrometric precision in the single epoch images?
No, I'm not the right person to ask for this. But
okay.
If you shoot an email, I can forward it to the people that actually worked on the catalogs.
Okay, well, nice to know that maybe this can be done. Okay. If there are no more questions, we will now wrap this up. And this presentation will be available on our website and on YouTube's LIneA channel. And for the next week's webinar, we will have Santiago Avila from the Universidade Autónoma de Madrid talking about the effect of the galaxy halo connection on galaxy clustering in the advent of stage 4 experiments. So thank you everyone for attending, and a special thanks to Dr. Troester. Thank you very much for accepting our invitation.
Thanks for having me.
Okay, and everyone, have a great day. Stay safe, and I hope to see you all again next week. Bye-bye.
Thank you. Bye.
Bye-bye. Thank you.
Thank you.
Goodbye.